Hello again, folks, and welcome to our next module dealing with probability. This is the next piece of the puzzle towards that goal that we've had for these first several modules, which is again putting together a framework to distinguish statistically significant results from inconclusive or insignificant results, and to use that to test hypotheses. So back here behind me, I've got our old friend, the normal distribution, or at least what's supposed to be one. That there's no way that's symmetrical. You'll figure out pretty quick why I don't do a heck of a lot of board work. But remember that last time with z-scores, we figured out how to use the normal curve and to use that standardized process of calculating z-scores to basically place any individual score somewhere on this distribution, and to do things like calculating the percentage of entire populations that are above that score or below that score. Or we can take a percentile that we're interested in, and we can identify the minimum z-score it would take to be in that area of the distribution, what we might call a threshold, the border of that portion of the distribution. So we might be interested in this shaded area here. We can, while knowing very few things about the population, make very specific estimates about the percentage of that population that is in that shaded area, that's above that specific z-score, or again, the z-score that matches with those percentiles. So the last piece of the puzzle, again, involves using this normal curve and using the characteristics of probability to, again, assess whether we consider results to be meaningful or not. More to come on that, but first we're going to start with some basic descriptions of probability here, and including how to calculate simple probability. So again, we use those standardized z-scores. We can compare totally different distributions. We can do those proportions. We can find those threshold scores. Now, again, we move ahead by talking about probability. So probability. Lesson 1 on probability. Are you ready for lesson 1? Here you go. It's almost life lesson 1. People are really bad at probability. People suck at calculating probability. Not every single person, but as a group, we are very poor at calculating probability. There are entire logical fallacies named after mistakes people make when estimating probability. For example, the gambler's fallacy. Gamblers tend to believe in streaks for things that are not necessarily related. They think, oh, I'm on a hot streak now, so I need to keep gambling so that I can keep, making all this money. Or, oh, I haven't won in a long time, so I'm guaranteed to get on a hot streak sooner or later. Both of those things are false. Both of them involve confusing events that are unrelated, like what card comes up in a deck or how a roll of a dice turn out, and assume that they are related, that past outcomes predict future outcomes. We make that mistake constantly. We also make the mistake of assuming that the outcomes of probabilistic events are driven by things other than probability. So, for example, a lot of people who gamble, and notice I keep mentioning gambling, it's pretty much a place for people who aren't great at probability. People who gamble oftentimes believe, well, because they're a good person, that things are going to turn out well for them. It doesn't matter. That slot machine, when you pull the handle, it has no way of knowing if you just saved a box of kittens from a fire or if you just threw a box of kittens in a fire. The probability is the same. It is mathematical. It does not change, no matter how much we try to project our biases into it. There are entire industries devoted to people who are good at probability taking money from people who are bad at probability. Gambling and insurance are probably the two biggest examples of that, but it entirely involves using the rules of probability to gain an advantage for the house or the insurance provider. So here's an interesting little chart that illustrates one kind of fallacy that people fall into. People tend to round probabilities down. They round it either down to 0%, up to 100%, or if it's somewhere close to 50%, they will consider it a 50-50 shot. Those are the round numbers that we really like. What this leads to happening is people lose faith in a lot of probabilistic predictions because they don't realize they're doing that rounding process. So for example, if a weather model tells you it has a 10% chance of raining today, people are going to round that down and say, okay, it's not going to rain today. And then if it does, they're going to say, oh, the forecast was wrong. No, it wasn't. The forecast is only wrong if those 10% predictions happen less or more than 10% of the time. Those things should be happening 1 out of every 10 days they're predicted, but people don't think that way. Or when a 95% chance of something when it fails. You expect that to happen 1 out of every 20 times, but people's conclusion is 95% is basically 100%, so the model must be wrong. Again, interpretation of probability is a problem for a lot of folks. But let's get into the definition itself and how to calculate it. Probability is related to that idea of frequency. Remember, we've been making all these frequency distributions. The normal curve is a frequency distribution. Probability, again, compares the relative frequency of some kind of an outcome, some kind of possible result of an event, the flip of a coin or something like that. Probability, again, is imperfect, especially for estimating small sample sizes. You can, if you roll a die and you say, what are the odds that it's going to come up 1 through 5 on a 6-sided die? You have a 5 out of 6 chance that will happen. If you roll that die and it comes up 6, that doesn't mean your probability calculation was wrong. It just means you got the improbable event. So relative frequency is all about, if this event kept happening over and over and over and over again, what's the relative frequency of the event we're looking at? If you rolled that die 1,000 times, the percentages of 1 through 5 would be much closer to probability than if you rolled it simply once. So how often will the outcome we're interested in happen relative to everything that could happen? Here's where this ties into the big picture. Scientific research, again, involves making conclusions based on probabilities. Again, we always have uncertainty baked into the mix. Remember, we said we don't use the word prove for research results. That's because we never have 100% confidence and we never have 0% confidence. We're always somewhere in the middle. There's always a chance that we are wrong, no matter how powerful or how strong the pattern of data is. So probability is at the heart of this idea of statistical significance. Again, the underlying idea, even if your hypotheses, your predictions are wrong, if you correlate two variables, they almost always will correlate at some number that's not 0, even if they're unrelated in the population. If you measure an experimental and a control condition on an independent variable, they're not going to tie. At least it's very unlikely they will. They almost certainly will be at least a little bit different. How far apart do they have to be before we can say this represents something that's really happening at the population level, versus saying, well, there's going to be a difference there somewhere. This is so small that we shrug at it. Again, we can't just eyeball it and decide. Too many biases there. We need a standard. The probability of the results that we observe provides that standard. And the question that we ask, which we'll talk about in much more depth in the next module, how likely is it we'd see a result like this if our predictions were wrong? A lower probability suggests there's less of a chance our results are a fluke, but still not a 0% chance. That's what allows us to conclude statistical significance. So statistical significance is an inferential statistic that's based on a lot of different descriptive stats, one of which are these probability estimates we're going to learn. As the observed patterns in the data become stronger, it's more likely to represent a meaningful relationship at the population level. Correspondingly, the probability that the prediction was wrong goes lower and lower and lower as our patterns of data become stronger and stronger. Again, what a lot of this revolves around is that idea that I've talked about a couple of times called thresholds. On those normal curve exercises where we picked a percentile we were interested in, we said, what's the minimum z-score you need to be in this area? That is finding a threshold, a border. Anything beyond this line has a lower probability than our threshold of happening. So we're going to consider anything beyond this line statistically significant. Anything that's not beyond this line has a higher probability than our minimum, and so we call them inconclusive. So again, it's really similar to that normal curve stuff that we've done in the last module. So here's how we calculate probability mechanically with a formula. We're going to learn a little more about this in the next talk. First, figure out what the number of possible successful outcomes that can happen. Successful outcomes is in quotes because it isn't necessarily something that's good or a success. You might be interested in the probability of someone contracting a disease, and we wouldn't consider that a success, but that's just the term that we use. So say we're flipping a coin, and say the successful outcome, the one I'm interested in, is that it comes up heads. How many different ways can it come up heads? Exactly one. There's only one successful outcome there. Then you find the number of all possible outcomes, including those successful outcomes. Okay, how many things can happen when you flip a coin? 2 things can happen. Maybe some smartass out there is saying it's going to land on its edge. Maybe that's not going to happen. It's going to come up heads or it's going to come up tails. Stay with me. All right. Then you divide the first number by the second number, and that's it. Probability of getting heads when you flip a coin, there's 1 successful outcome. There's 2 total outcomes. 1 divided by 2 is 0.5 or 50%. Probability of drawing a heart out of a deck of cards at random, there are 13 successful outcomes. There's 13 hearts in that deck. 52 total cards, 13 by 52. There's a 0.25 or a 25% chance that you'll draw that heart. So probability estimates always range between 0 and 1. If you somehow get a probability estimate that's somehow negative, I don't even know how that would happen, but greater than 1, you have made a mistake. Go back and readdress it. You'll oftentimes see probability expressed in research articles with this little lowercase p. Again, you oftentimes will see that compared to a number like 0.05 being below or above that line. In more recent articles, you're more likely to see a precise number. What that probability is what's the probability we would have seen a pattern like this if our predictions were wrong? So the lower that is, the stronger the researcher's case is. Again, much more on that in the next module and modules to come. So let's do a quick review of how this looks in practice, and then we will wrap things up and move on. So let's say we've got a roulette wheel here, and if you're not familiar with the roulette wheel, there are 36 equally sized slots. You spin a ball around the wheel as the wheel spins, and it's going to land in one of those spots. It has an equal chance of landing in every single one of them. There are 18 red spots, 18 black spots, and 2 green spots. So let's say we wanted to say, what's the probability of the ball landing on the number 5? Well, no numbers are repeated. Number 5 is right over here. So there's one successful outcome there. There's one outcome that's consistent with landing on 5. How many total outcomes? The 38 spots on the wheel. We divide 1 by 38, and we find we have a 0.0263, or if we convert it to a percentage, a 2.63 chance the ball will land on a 5. It's a 1 in 38 chance. Here's the trick, and here's how gamblers make their money taking advantage, or excuse me, casinos make their money taking advantage of probability. If you go to a casino, you make this bet and you win, yeah, you won, your 1 in 38 shot hit. They will pay you 36 times what you bet. They will pay you as if it was a 1 in 36 chance, not 1 in 38. That difference is where they make their money. It means over enough spins of the wheel, they're essentially printing money. They are going to come out ahead in the long run. So you can calculate these along. I'll pause for just a second, and you can pause the video if you want to calculate them on your own. But what is the probability of a ball landing on a red spot? Well, there are 18 red spots there. So pause. Again, the way to do this is to divide 18 by 38, and you will find about a 47% chance that that will happen. I'm going to check along on my own calculator. 47.4% chance. What's the probability of landing on a green spot? Well, there's 2 green spots, 2 successful outcomes, divided by, again, the same 38 squares that were always there. You will get a 5.26% chance. Again, the casinos will pay you as if the odds were somewhat better than they actually are. That is where their mathematical edge comes from. But here, this is also just an illustration of how we can use this sort of setup to make basic probability calculations. More to come on that practice quiz. But for now, we are done with basic probability. We are going to progress a little farther by talking about how it connects to different forms of sampling. I will see you there.